So we already know how to write down the Fourier series of a function. The Fourier series on the interval from negative L to L is a constant a0 over 2 plus the sum going from 1 to infinity of constants an times cosine functions of this form plus bn times sine functions of a similar form. So we've already seen how to find the Fourier series. In this video, I would like to express this a little differently using complex numbers. So this will be the complex form of a Fourier series. It all stems from this fact: e to the it is cosine t plus I sine t, a fundamental relationship known as Euler's formula. Now, what this means is that I can take cosine t and write it as purely exponential functions. In fact, I have cosine t is really equal to e to the it plus e to the negative it divided by 2. You could see that if you take this expression, add it to the same expression where you just replace the I with a negative I, and then add, you'll get the sine t's canceling 2 cosine t. So then when you divide by 2, you just end up with cosine t. So it's a different way of writing down this identity. And similarly, sine t is equal to e to the it minus e to the negative it divided by 2i. So doing similar logic, starting with Euler's formula, you can get this expression for sine t. So I'm going to use these facts and rewrite my Fourier series. So I still have this constant, a0 over 2 in front, but now I'm going to write things down where cosine is replaced with this identity and sine with that identity. So I have a constant, an. Then I'm going to get e to the I n pi over Lx plus e to the negative I n pi over Lx over 2, and a similar expression for sine, bn times e to the I n pi over Lx minus e to the negative I n pi over Lx divided by 2i. So we have a0 over 2 plus the sum going from 1 to infinity. Now I'm going to group all the terms that have an e to the positive power, and then I'll group all the terms that have e to the negative power. If you group all the terms with a positive power, I think you'll find 1/2 an minus I bn times the positive terms, e to the I n pi over Lx, and the terms that have the negative would have coefficient 1/2 an plus I bn times e to the negative I n pi over Lx. It might look like I mixed up the pluses and minuses, but I didn't, because here I'm dividing by an I, and that's the same thing as multiplying by a negative I. Now I'm going to just call this constant Cn, and I'll call this constant C negative n with a negative subscript because it corresponds with the negative powers of e. And I'm going to call this constant C0, so just renaming everything. I get the complex form of the Fourier series. So the complex form of the Fourier series is this. Instead of summing all positive values of n and having both positive and negative subscripts, I'm going to just sum over all values of integers. So I'm going to start with n going from negative infinity to infinity. This is our notation for just summing up all integer values of n. Then I'm going to have Cn times e to the I n pi over Lx. This is a nice, simple expression. It's known as the complex form of the Fourier series. So what are the coefficients? Here, the coefficients Cn are given by this expression. So Cn is 1/2 an minus ibn. Now, if you write down what an and bn are, you get 1 over 2l. an and bn both have a division by l in them. The integral from negative l to l of f of x cosine n pi over Lx dx, that's the first an term, and then I'm going to subtract I times the integral from negative l to l, the same function f of x, times sine n pi over Lx dx. But if you notice, I have cosine minus I sine. Using Euler's identity right back up here, this Cn can be expressed as 1 over 2l, the integral from negative l to l, my function f of x times e to the negative I n pi over Lx dx. So the complex form of the Fourier series you'll sometimes see, because it's such a nice, simple expression, is here where the coefficients Cn are given by this integral. All right, excellent.